So today I'd like to take a little bit of time to show you how they would have used logs back before the calculator to do more complicated mathematical processes. I then want to show you how logs are still used today to create meaningful graphs from data that might otherwise not be easily interpretable. All right? So first, math without a calculator. So what I'd like you to do is just get an estimate of the answer for x based on our simple log tables with just 9 or 10 numbers. All right? So I'm not expecting you to be accurate. I'm expecting you to have a range of numbers and know that our answer lies somewhere in between. Okay, so for instance, if I said, what number has a log whose number is 3.815? Hopefully you would see the 3 and say it's going to be in the thousands. And then I hope you look at the 0.815 and say it's not on our chart, but it's somewhere between these two. So that would mean that this answer would be between 6,000 and 7,000. That's all I want you to be able to do. So try doing these other three and see if you can establish the range that our answer would be. This should be in the hundreds, the millions, and the tens. You look and see where it falls. We're somewhere between 1 and 2. So that means somewhere between 100 and 200. This is going to be in the millions. It's going to be somewhere between 5 and 6 mil. This guy is going to lie somewhere between 8 and 9, and since there's a 1 there, it would be somewhere between 80 and 90. Again, not super accurate, but at least you now have some idea of approximately where your answer lies. Okay, so earlier we had talked about these. You had done these yesterday. I would now like to take the answers we got from yesterday and try to estimate where our answer would be. So for this one, we know that that is 16. But let's say we didn't. Let's say it was a really hard thing to evaluate. We could get a rough idea of what this was going to be by looking at this and saying it's in the tens and it's somewhere between 1 and 2. So it's somewhere between 10 and 20. And again, we know it's 16. This one, though, we would have no hope of figuring out what range that is in. That's 7 times 7 times 7 times 7. I get lost after the second one. But we can look at this and say, oh, that's going to be in the 100 millions. And then we can look at this number and say it's going to be somewhere between the 200 and 300 million mark. All right, so that would give people a real good estimate of what would have been a really time-consuming math problem. Finally, with this one, we might not be able to do that in our head, but we could have done the logs in our head, and we did. Then we can look at this and say, oh, this is going to come up in the 10 range. Okay, in the 10. So let's see. 3, 5, 2. So it's actually somewhere between 20 and 30. All right, so 90 divided by 4 should be somewhere between 20 and 30. And you can see we've narrowed down our possible answer to these into a range of numbers. They quickly realized that by having more than just 10 numbers that they knew the logs of, they can become more accurate. So they would create these things called log tables, and people would have to carry them around to be able to do their mathematics. And it actually wasn't too bad, and it gave them pretty decent answers in a pretty short amount of time. So here is a blown up version of part of it, and I just want to show you how we'd work it. So I'm going to take a number that's not too obnoxious to multiply, but we're not going to do it like we did in 3rd grade. We're going to use the idea of logs. So we know that this number, whatever it happens to be when we multiply those together, will be the same as the log of 131 plus the log of 152. Okay, so for 131, what we would do is we'd go 131 We find the first two digits here, the next digit there, and that log number would be this thing right here. Okay? We know this is in the hundreds, so it should be 2.1173. I hope you understand I got the 2 because this is in the hundreds. I got the 1173 because that's where 131 meets up. And then do 152, same way. 152 would be 1818. 2 because we're in the hundreds, 1818. Again, I turned multiplication, a pretty difficult multiplication, into a pretty simple addition. 1, 9, 9, 2, 4. Okay, again, I'm not at my answer yet, but I'm almost at my answer. So now I know that my answer is going to be in the 10,000s. Where in the 10,000s? I looked for this. And I find a number really close to that right here. Okay, so I can look at that and say I'm going to be somewhere around 199. Well, actually, I know I'm in the 10,000, so I need to add 2 more zeros. These two numbers multiplied together gives me almost 19,900. And again, back before the calculator, this was a really quick way of getting an answer without having to go through the laborious process of multiplying out the entire sequence of numbers. The bigger these numbers were, the more useful logs became. So now if we try this on our calculator, we see that multiplying them together gets us 19,912. We were only off by 12, okay, without having to multiply at all, just by adding. So we turned a difficult multiplication into a simple addition. Logs were amazing. Again, you're probably not going to have to do that, although there are times where the numbers will be too big to work in your calculator. And you may have to resort to logs to figure out what's going to happen when you combine those numbers together. But logs really shine, and still shine really brightly, when we look at graphing numbers that extend over a very wide range. So for instance, if we are looking at the population of the Earth over time, and we're going to start in the year 10,000 BC, and we look at the population in millions, and then graph it, you'll notice that for most of Earth's history, the data points don't even show up. The numbers now are just so large that those original numbers kind of get lost in the shuffle. Well, logs help rescue us from this graph that really is not that meaningful to us because we can't see half the data. And what we know about logs is logs can take a big range of numbers, like numbers that range from 1 to a trillion, and shrink that down to numbers that run from 0 to 12. So it takes a big range of numbers and turns it much smaller. So you go in there and you switch. Let me show you that again. We go into our vertical axis, and almost all graphing software is going to allow you to graph it on a log scale. And when you do that, all of your numbers show up. Because if you notice on a log scale, the numbers don't go up by equal intervals, but they go up by powers of 10. All right, so each block represents an increase of 10-fold. All right, now all our numbers show up. This might give us a better representation of what's happening with the population, but by going and looking at it like this, these slopes on the log scale become what are called your growth rates, which are really important numbers to know. Okay, so again, here's the two things. This is the raw numbers, this is the log numbers. These type of logarithmic graphs have been something that you'll see a lot in the last year, because when COVID was being studied and is being studied, oftentimes places like Johns Hopkins would be plotting out their graphs logarithmically. Why would they do that? Because there's a big range of numbers. And in order for all the numbers to show up on the graphs, the logarithmic scale makes more sense. However, if you're not familiar with logarithms, these graphs might convey information that isn't really true. So when you look at these, you might look at the United Kingdom and it might look like a nice steady growth, a linear growth. But realize that when we go from here to here, that represents 9,000 new cases. But when we go from here to here, the same distance on the graph, it represents 90,000. Okay, so it appears that the growth is steady, and it is on a logarithmic scale, but in real life it's compounding. It's 10-fold larger than it was before. So you gotta be careful when you're looking at these that you don't get the wrong interpretation. Again, these scales are very good because our slopes tell us our growth rate. But when we look at them on a non-logarithmic scale, we can just see how quickly things are getting out of control. Okay, so again, this is the logarithmic plot. This is the non-logarithmic plot. The advantage to the logarithmic is all the data gets spread out and we can see a wide range of numbers. Okay, it's also very useful because it lets us calculate growth rates very easily. But be careful that you can identify a logarithmic graph and you understand that it does not work the same way as a normal graph does. Going from here to here is a 10-fold increase, and going up to here is another 10-fold increase. Okay, it's not going up by the same raw amount, but by the same multiple. All right, so it's much worse growth than what it appears on the logarithmic graph. Next time, we've had a 3-day detour. We're going to go back and we're going to see how all of this applies to sound.